What is light? It took until the middle of the 19th century before some of the basic questions were answered.
The light of our lives comes from the sun and other stars. A form of electric and magnetic energy, photons of light travel through space, behaving both like particles and waves. Like ripples in a quiet pool of water, changing electric and magnetic fields of light can be seen far away from their point of origin. Light travels at a constant speed for hundreds, thousands, even millions of years to get here. There's distant light in the universe, billions of years old. Even the light from the star nearest our sun, Proxima Centauri, takes 4.3 years to arrive, and that's traveling at 186,000 miles per second, the fastest speed in the universe. To collect light, our eyes function something like cameras, with lenses and pupils controlling the amount of light absorbed. Much of the light in space is too distant for our eyes to see detail and color without assistance. To peer farther into space, Galileo pioneered the use of a telescope in 1609. Images were magnified with an eyepiece. These early telescopes collected no more light than modern binoculars. To see farther, these telescopes would need to become larger, but they could only grow so much. As better and better telescopes help us capture light farther and farther away, we can see light older than man and as old as the universe.
What is the universe made out of? They thought it was earth, air, fire, water. But if that's what the world is made out of, then what is light? You can't put it in a box, you can't shake it, you can't touch it, it's ephemeral, yet it's everywhere. Light is everywhere and nowhere. Everyone experiences the epiphany of light. But the question is, what is it? And that is dogged physics for thousands of years.
Dogged physics? Doesn't that just make your day, though? Isn't that a reason to come to the office?
That's right. That's why some of the greatest minds, going back to Isaac Newton, made the first definitive studies on the nature of light. Newton, for example, took white light from the sun, shone it through a prism, and showed that all the colors of the rainbow would come out of white light, showing that white light is really a composite, a sum of red, orange, yellow, blue light.
Didn't he also recombine it?
That's right. He could also show that Roy G. Biv, red, orange, yellow, the violet, could be recombined to create white light. So Newton thought that light was in some sense particulate, little tiny corpuscles, as he called it, made up the stream called light. So we had the first theory of light, the fact that light is based out of particles. But however, there was an alternative theory, a rival theory to Newton's theory, that said that light was a wave. And there was a guy named Young who many years ago was able to show that light had wave-like properties. Think of surfing, for example. Every surfer knows that you could ride on an ocean wave, but if a second ocean wave comes at you from another angle, the two waves interfere, giving you an interference pattern, and then of course, if you're not careful, you wipe out. Well, Young showed this with light. He was able to get light, shine it through a small little pinhole, get another pinhole of light, and have these two waves collide with each other, and there it was, a beautiful interference pattern. So we now had two rival theories of light, the Newton corpuscular particular theory of light, and Young's and others' wave-like theory of light.
Now, Einstein took this the next step.
What Einstein said, and this is the genius of Einstein, he said, perhaps both are right. Perhaps Newton showed us that light has particle properties, and that Young showed that light has wave-like properties, and the two are different manifestations of the same thing. Think of like looking at an elephant. You touch the trunk, you think the elephant is a snake. You touch the legs, you think the elephant is a tree. And yet the elephant is a merger of all these qualities. So Einstein introduced the concept of duality, particle and wave-like duality.
For the ancients, science was grounded in observation. Even today, many of the questions science attempts to answer begin with an unusual sight. But we would not be able to make observations or see the world at all without light. But what is light? We can't touch or taste or hear it, And usually, we can't even see light completely on its own. We see light as it is filtered through the atmosphere and reflected off different surfaces. To understand light, we need to understand a larger group of energy, known as electromagnetic waves. Light is a very small part of the electromagnetic spectrum, and all the types of waves in this spectrum share certain properties. All forms of electromagnetic energy, including light, are waves. And as waves, they all have frequency. Frequency is usually defined as the number of waves that pass a certain point in a second. The difference in frequency is a result of the size of the wave. A longer wavelength corresponds to a lower frequency.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum.
An immense scale we use to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame and over 2,000 miles of tape, and it's everything that the human eye can see. The importance of this frame is that stars emit almost all of their light in this part of the spectrum.
And even though the light is visible, it still contains hidden tools. The secrets are in the spectrum itself. The visible light in this lamp comes from hydrogen gas excited by electricity to form a glowing plasma, similar to what happens in a nebula. By viewing the lamp through a diffraction grating, we can split the light up into 3 narrow lines on the spectrum, a virtual fingerprint of light, unique to hydrogen alone.
So in the spectrum, you see 3 features. One is red, one is a light blue, and the other is a deep blue. This pattern of wavelengths is absolutely unique to hydrogen, and there's no way to confuse hydrogen in the spectrum with any other element.
An electron in the lowest energy shell in an atom can be struck by and absorb the energy of a photon, giving it enough energy to jump to the next energy shell. And the reverse process allows the electron to jump back down into the lowest energy shell and emit a photon. The color of the photon depends on the energy difference between the 2 shells. This explains the spectral lines that identify an element. Since white light contains all the colors in the spectrum, when we shine white light on a sample of an element under the right conditions, the atoms absorb all the photons that allow their electrons to jump to other energy shells. So, the absorption spectrum is all the colors in white light minus those that match the difference in energy shells within the atom. And when those electrons spontaneously jump back down to the lowest energy levels, that emission spectrum contains only the lines that match the difference in the energy shells within the atom. Here is a piece of spectra from hydrogen. The primary quantum number n is shown on the right alongside the line representing that energy level. When an electron jumps from the n equals 3 shell to the n equals 2 shell, red light is emitted. When an electron jumps from the n equals 4 shell to the n equals 2 shell, aqua light is emitted. When an electron jumps from the n equals 5 shell to the n equals 2 shell, blue light is emitted. When an electron jumps from the n equals 6 shell to the n equals 2 shell, violet light is emitted. When an electron jumps from the n equals 7 shell to the n equals 2 shell, ultraviolet light is emitted. No jumps to n equals 1 are shown because they are all in the deep ultraviolet.
Light is part electricity and part magnetism, and it travels like a wave. All waves, waves of water, waves of sound, waves of light, waves of whatever, have wavelengths and frequency. Because light travels like a wave, we can measure the wavelength and frequency of light.
Wavelength is the distance from one peak of a light wave to the next.
Frequency is the number of wavelengths that go by a certain point in 1 second.
When you multiply the wavelength of a light wave by the frequency of the same wave, you'll come up with c, the speed of light. C is a constant. Since c is a constant, wavelength and frequency have an inverse relationship. If wavelength increases, then frequency decreases, and vice versa.
The speed of light is always 300,000 kilometers per second, no matter where you are or who you are.
If you don't believe us, consult Genesis chapter 1, verses 19 through 24. And God said, "Let there be light, which travels no faster than 300,000 kilometers per second." And it was good.
We measure light waves in units called nanometers, which are really, really small. How small are they? Well, about 1/billionth of a meter. A violet light wave is about as long as a bacteria.
Light comes in many different flavors, which we identify by their wavelength. All of the wavelengths we can detect make up what we call the spectrum. Some of the wavelengths can be hundreds of meters long, and some of the smallest wavelengths are smaller than the size of an atom.
We can only see the part of the spectrum in the wavelengths between 400 and 700 nanometers. We call this range visible light. Makes sense, doesn't it? Visible light is all the light in the Roy G. Biv rainbow, but there's a lot more light out there radiating around us than just our familiar visible light.
The entire spectrum starts with gamma rays, which have the most energy and the smallest wavelength. Then, going down in energy, we have X-rays, ultraviolet light, visible light, infrared, microwaves, and finally, radio.
Gamma rays have the highest frequency of all light, and so their wavelength is really small. But remember what we said about frequency. Higher frequency waves have more energy. Gamma waves are so small and have so much energy, they can bust through just about anything.
Ultraviolet rays are the ones that cause sunburn. Luckily, we still have enough of an ozone layer on the Earth to prevent the ultraviolet rays from cooking us. Infrared light is heat radiation, and radio waves include TV transmissions and AM and FM broadcasts.
One last thing you should know about light. Light is sometimes called radiation. So if we say infrared radiation, we mean infrared light.
Let's review. Light is energy that moves like a wave and interacts like a particle. A particle of light is called a photon. The speed of light always stays the same, 300,000 kilometers per second. The frequency of light multiplied by its wavelength will always equal the speed of light. To find the amount of energy in one photon, you use Planck's equation, which is energy equals Planck's constant times frequency. Higher energy light has higher frequency and shorter wavelength. Lower energy light has lower frequency and longer wavelength. The full range of light is called the spectrum.